You know, when you look up at the night sky, assuming you can actually get far enough away from the city lights to see it, I mean, the most overwhelming part isn't really the stars.
Right, it's the space between them.
Yeah, exactly. It's just this staggering amount of nothing, just this endless, freezing, completely empty void.
Oh, that is definitely the intuitive way to look at it,
Right, because we're taught from a young age that space is just, well, space, like a giant cardboard box where the planets and stars just kind of live and move around.
It makes sense we'd think that way. We move through air, which we know is made of molecules,
Yeah.
right? But when we look at the cosmos, we assume it's just the ultimate passive background.
Like a blank canvas.
Exactly.
Yeah.
Just a stage where mass and energy perform. But that
Yeah.
assumption is fundamentally flawed.
And that brings us to the core of what we are doing today. What if we've been looking at this completely backward? What if you, the listener, and I have been totally misunderstanding what that empty void actually is?
Because the theoretical physics we're looking at today suggests that empty space isn't empty at all.
Right. What if it's not a container, but like a highly complex programmable machine?
That is exactly what the math is pointing toward.
And what if instead of building bigger rockets with, more explosive chemical fuel to push us through that space, the future of aerospace involves hacking the literal fabric of reality?
Making the space itself do the moving. I know, it sounds like we're pitching a science fiction film right now.
It really does sound insane.
But this concept is sitting right at the bleeding edge of theoretical physics. We are inching away from chemical propulsion, which is basically just throwing controlled explosions out the back of a tube.
A really expensive tube.
Right. And we are entering the theoretical era of what we call metric engineering.
Okay, let's unpack this, because this is the mission for our deep dive today. We are exploring the theoretical and mechanical frontiers of metric engineering.
Specifically through a mind-bending framework known as quantum truss spacetime, or QTS.
QTS, right. So we are officially tossing out the rocket fuel today. We're going to look at how advanced aerospace tech might manipulate the vacuum of space itself for interstellar travel.
And do it without the occupants feeling a single G-force.
Which is wild. But I want to ground this immediately for you, the listener, because when you hear hacking reality, you probably assume we're diving into some internet conspiracy theory.
Oh, absolutely not. We are dealing with real, peer-reviewed physics here.
Yeah, the sources we're pulling from reference Nobel laureates, like T.D. Lee and Frank Wilczek. These are the people who helped define modern physics.
And they established that the vacuum is the central energetic structure of everything. Wilczek even questioned if space itself is the primary reality and matter is just a secondary manifestation.
Wow. Wait, really? Matter is secondary?
According to this view, yes. What's fascinating here is that T.D. Lee actually coined the term vacuum engineering.
A vacuum engineering? That just sounds cool.
He stated that if we can alter the vacuum, we might encounter totally unexpected phenomena. The key proof is that empty space is boiling. It's churning with quantum fluctuations.
So it's not just a void?
No, it's structured by an underlying space-time metric that encodes what we feel as gravity. It has physical properties.
And if it has physical properties, I mean, theoretically, it can be engineered, just like steel or silicon.
Exactly. But to understand how we travel through it, we first have to redefine what space actually is.
Right. Which brings us to the quantum truss spacetime framework, the QTS model.
This is where we take Einstein's smooth fabric of space, that rubber sheet analogy, and we zoom in.
Way in, right. Because I love this concept. It says, hold on, if you look close enough, it's not smooth at all.
You have to look at the microscopic fundamental quantum level. The QTS framework argues that the universe is a discrete, self-organizing computational lattice.
So it's made of parts.
Yes, microscopic nodes connected by what they call entanglement struts.
Okay, so let me visualize this. Instead of a flat bed sheet, it's more like a microscopic cosmic jungle gym.
That is a highly accurate way to visualize it, yeah. A densely packed three-dimensional grid of physical connections.
And this jungle gym isn't just sitting there.
No, it is actively computing the geometry of the universe from moment to moment. It's the source code of physical reality.
And this source code uses two master variables, right? The first one is stiffness, which is the Greek letter kappa.
Correct.
That's
Kappa. You can think of it mechanically.
like how hard a metal spring is to pull apart.
Very similar, yes. In a quantum context, Stiffness is the coupling constant for gravitational degrees of freedom.
So it's like the inverse of Newton's gravitational constant.
Precisely. It determines exactly how resistant the space-time lattice is to being bent or warped by mass and energy.
Okay, so if I put a bowling ball on a tight trampoline, the stiffness dictates how deep the ball sinks.
Right. And then you have the second master variable, which is strut strength, represented by gamma.
Strut strength, what does gamma do?
While kappa is about resistance to bending, gamma governs the entanglement entropy cost. You might need to translate that one. Entanglement entropy cost sounds like a lot of physics jargon. Fair enough. Every connection in that cosmic jungle gym requires fundamental quantum energy just to maintain its structural integrity. It isn't free.
Oh, I get it. So gamma is the energy bill for keeping the universe intact.
Basically, yes. It's the restorative force, the inherent tension that keeps the lattice from unraveling into nothingness.
So we have the stiffness, kappa, and the energy keeping it together, gamma. And our sources say that for our universe to exist, these two have to be in a perfect balance.
A literal Goldilocks zone. Because if it falls out of balance, the consequences are apocalyptic.
Like phase transitions of space-time itself. So what happens if kappa drops too low?
If stiffness drops too low, the truss loses structural coherence. The entanglement struts can't hold tension.
And then what?
The universe effectively melts into a high-entropy quantum gas. There's no consistent geometry, no distance, no time.
Just a chaotic soup. That is terrifying.
It is total geometric collapse. But what if kappa is tuned way too high?
Does it freeze?
Exactly. It freezes into a rigid, non-relativistic crystal. It loses all the flexibility required for Einstein's general relativity to work.
So gravity wouldn't function smoothly. Light wouldn't bend around stars.
Right, the whole system would basically seize up. But in our Goldilocks zone, the lattice behaves like a liquid-like space-time.
Perfectly balanced. Flexible enough to bend for gravity, but strong enough to keep cause and effect working.
Which is why we exist to talk about it.
You know, reading this, it made me think of being a system administrator for a video game engine.
Ooh, I like that analogy. How so?
Well, if you play a game and want your spaceship to move, normally you apply a digital force to the character. You push the joystick, you get thrust, you move through the static map.
Right, the classical Newtonian action and reaction.
But metric engineering feels like hitting the developer console key and rewriting the game's core code. Instead of moving the character through the world, you change the math of the environment itself.
So the map moves around the character. Yes, that's it perfectly. You are hacking those lattice parameters to relocate the object.
Bypassing the whole pushing through a medium thing entirely.
But that raises a philosophical question. If space is this jagged grid of microscopic pixels, why does it feel so smooth to us?
Yeah, if I wave my hand through the air, I don't hit a rigid grid of entanglement struts.
Right, and Einstein's continuous math works flawlessly. This contradiction is answered by the renormalization group flow.
Renormalization group flow. Okay, what is that?
It explains how physical properties change across vastly different scales. At the absolute quantum level, it is jagged and chaotic.
But we aren't microscopic.
Exactly. As you zoom out to a macroscopic human scale, the math shows these discrete fluctuations average out.
Oh, it's like standing with your nose against a big TV screen.
Yes. Up close, you just see blocky red, green, and blue pixels.
But when you step back into the living room, your eyes naturally average it all out into a perfectly smooth photograph.
That is a perfect terrestrial equivalent. The jaggedness becomes mathematically irrelevant at large scales.
So general relativity just emerges naturally from this microscopic network. The discrete code perfectly mimics a continuous canvas.
Exactly. So now that we have the canvas, we have to figure out how to paint on it.
Right. How do we actively program this lattice to create movement and gravity? Which brings us to the metric tensor.
The metric tensor, represented as G mu nu. It is the primary mathematical tool for measuring spacetime intervals.
G mu nu. Okay, that sounds super intimidating. Let's simplify that. What actually is a metric tensor?
Think of a perfectly square grid drawn on a flat sheet of paper. The metric tensor is just the rule book that tells you the distance between the lines and how fast a clock ticks at any point.
Okay, so in flat, empty space, the rule book says a meter is a meter everywhere.
Right. Physicists call that Minkowski spacetime. The ledger is balanced. But the real universe is messy.
Because we have stars and planets messing up the grid.
Exactly. When you drop the sun onto that grid, it warps the lattice. It physically alters the values inside the metric tensor.
And the sources call that the Schwarzschild solution, right?
Yes. The mass of the sun stretches the spatial intervals and slows down the time intervals nearby.
And that's what we experience as gravity. Small objects just follow the curved pathways.
They roll down the geometric hills. They aren't being pulled. They are following the path of least resistance.
Which is wild. Gravity isn't a pull, it's just a warped grid. But from an engineering side, the sources mentioned the Reisner-Nordstrom solution.
This is where it gets highly promising.
Yeah.
This solution describes spacetime around a spherical mass that also has an electrical charge.
Okay, so if we add a massive electric charge to our grid paper, what happens?
The math shows the electrical charge creates contributions to the metric tensor that are opposite in sign to the mass.
Wait, so if mass makes a valley that things fall into, the electrical charge makes a hill. It pushes back.
In a localized sense, yes. It produces a repulsive effect on the spacetime geometry.
So anti-gravity.
Theoretically, yes. Electrogravitic repulsion. It proves gravity isn't a one-way street. If you manipulate the metric tensor, you can create localized hills and valleys.
Independent of needing a giant star. But what does this mean for building a ship? Are we just trying to create fake gravity?
We aren't just making a ship act heavy. We are aiming for directional curvature. We exert physical force on the lattice nodes to redistribute their entanglement entropy.
And the QTS framework calls this truss loading, right?
Yes. By injecting highly concentrated coherent energy into specific regions around the craft, you artificially increase the density of struts in front and decrease it behind,
So we are writing a temporary metric tensor around the ship.
creating an artificial geometric slope, the warp gradient, denoted by omega.
I love the rug analogy for this. It makes the math so simple.
It really is the most elegant way to illustrate non-Newtonian propulsion.
Because normally you walk by pushing your foot on the floor, friction pushes back, you move. That's a rocket.
Right, throwing mass out the back to move forward.
But if you stand on a long rug in a hallway, grab the front, pull it toward you, and kick the back away.
The rug bunches into a mountain in front of your toes and stretches flat behind your heels.
And you slide down the hallway. But you never actually took a step. Your legs didn't move relative to your center of mass.
That is precisely what truss loading does on a cosmic scale. The ship vigorously compresses the lattice in front, pulling the rug, and expands it behind.
So the ship just sits perfectly still inside this bubble, surfing the wave it made.
It's technically in free fall within its local coordinate system while the bubble migrates across the universe.
Which brings up a huge question. If we move the rug instead of walking, does the speed of light still apply? Can we break it?
This feels like cheating physics, but the math fully supports it. Einstein's special relativity says nothing can travel faster than light through spacetime.
Right. Through is the key word there.
Exactly, because general relativity places absolutely no speed limit on the movement, expansion, or contraction of spacetime itself.
So how does hacking the metric tensor let us cheat the rule?
It's about how metric coefficients affect measurements. Inside the bubble, the metric is flat. If an astronaut measures a laser beam inside the cabin, it's always the speed of light, c.
So their local reality is normal, no rules broken.
Right. But to an exterior observer on Earth, watching the bubble fly by, the effective velocity, VAL, can appear superluminal.
Faster than light. But how? How do I see a ship going 10 times light speed without the universe breaking?
Velocity is distance divided by time. The ship has altered its local spatial and temporal coordinates. The time coefficient, g00, is greater than 1, and the spatial coefficient, g11, is less than 1.
So the space around the ship is physically smaller and time is ticking differently?
Yes. You are dividing and compressed distance by an altered time. The space containing the ship is contracting and expanding faster than light.
And we know space can do this because of the Big Bang, right?
Exactly. During cosmic inflation, space expanded vastly faster than light. Metric engineering is just trying to localize that around a titanium hull.
Which is Miguel Alcubierre's warp drive concept from 1994.
Yes. His math proved you could construct an Alcubierre bubble for arbitrarily short travel times between stars, completely within general relativity.
But there's another massive advantage here. Mitigating inertial forces.
Biologically, this is huge. Conventional acceleration causes immense g-forces because your mass resists the push.
Right. Fighter pilots black out or die if they accelerate too fast.
But with metric engineering, the ship is perfectly stationary in its local frame. Zero proper acceleration.
Wait, absolutely zero g-forces.
None. You could go from 0 to 100 times light speed, make a 90-degree turn, and stop instantly.
And the crew would just float there, perfectly weightless.
Because relative to their pocket of space, they never moved.
It's like sitting in a perfectly still train car with a cup of coffee. Outside, a movie screen shows the world rushing by at fast forward.
And your coffee doesn't even ripple. The warp bubble is the ultimate shock absorber.
Okay, so the physics are sound, we get 0 Gs, we go superluminal, let's go build it. What's the catch?
The catch is a massive mathematical wall known as the Raisha-Toury equation.
Okay, let's take our time here. What is the Raisha-Toury equation and why is it ruining our plans?
It's a fundamental geometric theorem in general relativity, often used for black holes. It dictates that to force space to violently contract and expand like we want, you cannot use normal positive energy.
So I can't just hook up a giant nuclear reactor.
No. Positive energy pulls space inward. To force it to expand and repel behind the ship, the equation demands massive amounts of negative energy density.
Negative energy. Okay, is that just antimatter?
No, absolutely not. That's a common misconception. Antimatter has normal positive mass and energy. It just has reverse electrical charges.
If I drop antimatter, it falls down.
Exactly. Negative energy is a highly exotic state where a region of space has less energy than the absolute zero-point baseline of the vacuum.
A thermodynamic deficit.
Generating macroscopic quantities of this is the primary bottleneck of metric engineering.
And how much did Alcubierre's math say we needed?
Originally, to power a small ship, you'd need negative energy equivalent to the total mass energy of the planet Jupiter.
The mass of Jupiter. Yeah, that's a slight problem. We don't have Jupiter-sized batteries of a substance that barely exists.
Which is where our sources introduce bleeding-edge engineering concepts to get around it.
Using the Casimir effect, right, as a proxy for negative energy.
Yes. The Casimir effect is a verified quantum phenomenon. If you take two uncharged, highly polished metal plates in a total vacuum
and bring them super close together, like nanometers apart,
they spontaneously experience an attractive force pulling them together.
But from what? There's no charge, no gravity.
From the vacuum itself. The vacuum is boiling with virtual particles of all wavelengths. But the space between the plates is so restricted, the longer wavelengths can't fit.
They are geometrically excluded.
Meaning there are far more virtual particles bouncing around outside the plates than inside the gap.
So the quantum pressure on the outside is higher, pushing them together.
Exactly. And because there is less vacuum energy between the plates than outside, the energy density in that gap is mathematically negative.
Boom. Localized negative energy.
But it's microscopic.
Right. How does a tiny gap move a spaceship?
This is where the Eternum drive framework comes in, using recursive Casimir plasmonic amplification, or RCPA.
Okay, break RCPA down for me.
Imagine a spacecraft hull made of metamaterial. Billions of nested nanoscale Casimir cavities coupled with plasmonic resonators.
So a giant honeycomb of negative energy gaps.
Right. And they use a recursive feedback loop, bouncing specific frequencies of light back and forth to exponentially amplify those microscopic vacuum fluctuations.
It's like putting a microphone next to a speaker to get a massive feedback screech, but with space-time.
Conceptually, yes.
Yeah.
And models suggest this cascade effect could reduce the negative energy requirement by roughly 46 orders of magnitude.
46 orders of magnitude? That's insane.
It drops the requirement from a planetary mass down to about 10 to the 16th joules per kilogram of ship mass.
10 to the 16th joules. Is that achievable?
It's immense, roughly the energy of a multi-megaton hydrogen bomb, but it is a finite, physically achievable amount for an advanced civilization.
It makes it a solvable engineering challenge instead of mathematically impossible.
Exactly. And this energy delivery ties into the operational warp equation.
Ah, yes, the mathematical blueprint. W equals psi of omega, divided by tau, lambda, and sigma.
It's a fundamental operational equation. W is the warp effect itself.
So the left side is the speed, at the top of the fraction, the numerator is the engine, the bottom is the friction.
Let's look at the engine. Psi of omega.
Psi is the raw energy input, right? The phase-locked photonic energy. I pictured powerful rhythmic lasers.
Very close. It's highly coherent, perfectly synchronized energy directed to shape omega.
And omega is the warp gradient, the steepness of our space-time hill.
Correct. But the denominator is the resistance. First, we have tau.
Which is harmonic timing.
Yes. We are manipulating quantum fluctuations happening in femtoseconds. If your laser pulses your psi are even slightly off rhythm.
They don't stack right.
Exactly. High tau means sloppy timing, which kills the engine output. You need sub-femtosecond precision.
Because if you miss, you might shred the ship. Okay, next is lambda.
Lambda is membrane tension, or the stiffness of the lattice, like our Kappa variable.
So some areas of the galaxy are stiffer to warp through.
Yes. Lambda is the natural elasticity trying to snap our bunched-up rug back to flat.
And finally, sigma, background noise.
Space is incredibly noisy. Ambient radiation, cosmic microwaves, gravitational ripples, it all jiggles the lattice.
It's like drawing a straight line in a bumpy Jeep.
Right. You can't just turn the engine on. You must first create a localized null zone to actively quiet the local background noise.
You have to perfectly calm the pond before you throw the pebble in.
Absolute finesse, not brute force.
Okay, thought experiment time. Let's say we built it. We silenced the noise, fired the lasers, the Eternum drive is on. What is life like inside that bubble for the humans?
We look back at the metric tensor, specifically the coefficient for time, G00.
For superluminal travel, G00 is greater than 1.
Right. They enter an artificially accelerated time frame. Time flows drastically faster inside the bubble than outside.
So if I look out the window at a star, it looks like it's moving in slow motion.
Extreme slow motion. But locally, inside the cabin, everything feels normal.
But because G00 is elevated, there's a huge physical advantage, right? Energy scales up.
Yes. The baseline quantum energy states of all matter in the bubble are uniformly raised. The biological chemical bonds of your cells and the atomic structure of the hull become hardened.
Hardened, like I become physically bulletproof.
Relativistically, yes. The binding energy required to break your atoms apart is artificially elevated.
That's basically an invincibility cheat code.
It's a critical safety feature.
Yeah.
You could theoretically hit interstellar gas or even liquid water at high velocities without shattering.
Because the local metric fortified the titanium hull. That is wild.
Without it, high-speed travel would be suicidal for micro-impacts.
But what about the weird side effects? The sensory redshifting?
A direct consequence of the time differential. Since time is faster for the crew, any external signal entering the bubble gets stretched out.
Its wavelength gets longer, frequency drops.
Yeah.
Redshifting?
Like the Doppler effect, but caused by the stationary steepness of the spacetime metric, not velocity.
So a police siren driving away drops in pitch. What does it sound like in the ship?
If the gradient is strong, external sounds redshift. So far, they drop below the 20 Hz threshold of human hearing.
Complete silence.
Profound sensory isolation. You could rip through a planet's atmosphere and not hear a single sonic boom.
That's so eerie. But let's flip it. What does a bystander on the ground see when the ship flies by?
You wouldn't see a clear, shiny saucer. You'd see fluid optical illusions, driven by the variable refractive index.
Like how prescription glasses bend light.
Exactly. Every transparent material has a refractive index.
Yeah.
Water's is higher than air, which is why a straw looks broken in a glass.
But space is empty.
Classically, its index is exactly 1.
Oh.
But in metric engineering's TH epsilon mu formalism, the vacuum is a dense lattice,
So the architect changes the magnetic permeability and dielectric permittivity.
changing the actual refractive index of space. The warp bubble acts like a giant, invisible, moving glass lens.
Because the stiffness varies, it makes a gravity gradient, and Fermat's principle says light takes the quickest path, right?
Which is no longer a straight line. The light is mathematically forced to bend around the density.
So it looks like a highway mirage, the wavy lines off hot asphalt.
A perfect analogy. You'd see blurred boundaries and severe visual distortions radiating around the ship.
And if they turn it up, it leads to full cloaking.
Extreme gravitational lensing. It can bend background light entirely around the hull and seamlessly guide it to your eye.
Like water flowing around a rock in a stream.
The ship might just blink out of existence or look like a transparent, predator-like shimmer.
Not from cameras, but from actually bending the universe's light. What if they don't cloak perfectly?
Remember the spatial interval coefficient, G11? Because local space is compressed, a ship with a massive interior might look tiny to an outsider.
The ultimate Doctor Who TARDIS effect. Bigger on the inside.
A glowing Volkswagen Beetle on the outside, but a huge hangar bay on the inside.
Okay, this brings us to the everyday evidence. The forensic markers. If one of these crashes or flies over a farm, what does a retrieval team look for?
Not jet fuel or exhaust scorches. The most dangerous marker is intense radiation from hazardous blue shifting.
The exact mirror of the sensory redshifting the crew gets.
Yes, light or thermal heat radiating from the fast-time bubble out into our slow world gets heavily compressed.
Wavelength gets shorter, frequency increases, blue shifting, so a red indicator light on the ship looks blue.
More troublingly, the invisible infrared heat signature of the ship blue shifts massively into the visible spectrum.
It would glow super bright.
And during rapid acceleration, it shifts even further into ultraviolet or soft X-ray frequencies.
Oh, wow. So standing next to it, I'm getting hit by a silent wave of X-rays.
Without proper lead shielding, you'd suffer severe, immediate radiation burns. inexplicable sunburns with no radioactive isotopes in the soil.
That is a highly specific clue. What about temporal displacement?
An occupant might experience a 20-minute complex test flight, but radar on the ground only tracks them for a few seconds.
And the sources mention the Rip Van Winkle effect.
If the metric is reversed to slow time down for stealth, they might feel gone for an hour, but return to find weeks or years have passed.
Unexplained missing time. But the craziest forensic marker is the botany.
Forensic botany. If a ship with an accelerated time frame lands in a forest,
The plants are caught in the fringes of that fast time bubble.
exactly, the local environment's biological clocks accelerate to match the metric.
So if the ship sits there for 5 minutes in our time,
The grass beneath it experiences days, weeks, or months of metabolic processes. They age rapidly, consume nutrients, transpire water, and wither.
you'd find a patch of dead, severely dehydrated grass in a perfect geometric pattern.
A direct physical forensic indicator of a localized metric engineered field.
That grounds all this crazy tensor math into a dead patch of grass. It's brilliant. Are astrophysicists actually looking for evidence of this stuff in space right now?
Yes, through the mock data challenge.
Which is what?
A massive statistical analysis using Bayesian inference on the gravitational wave data from the LIGO and Virgo observatories.
The giant laser tunnels that detect black hole collisions.
They're using supercomputers to search the high-frequency noise for a lattice echo or a flicker.
What does a lattice echo look like?
If space is a discrete lattice of struts, a massive gravitational wave shouldn't be perfectly smooth. It should cause the lattice to jitter or breathe at a specific high-frequency harmonic.
Like a shockwave hitting a chain link fence instead of a rubber sheet, the fence rattles.
That is exactly it. They are looking for that rattle. If they find it, it proves the universe is an engineerable truss.
Moving all this from theory to practical reality, wow. We have covered a massive amount of ground today, redefining space as a computational lattice, tuning stiffness and strength to hack the source code.
Using the Casimir effect for negative energy to surf gravity waves.
Bypassing the speed of light, hardening atomic bonds to survive, feeling zero G-forces, all while the ship bends light and redshift sound. It's a total paradigm shift.
We go from being passengers to having the blueprint to be the drivers of reality.
But I know you have one final nugget for us from the Eternum Drive papers, the neurolinguistic quantum interface. What is that?
The math suggests that to perfectly stabilize this field, the system must tightly couple the local metric tensors with coherent quantum states, specifically neural quantum states.
Visual, like human brain.
The human brain's vast network of quantum coherent microtubules might already act as a natural low-level space-time modulator.
Wait, so the ship isn't flown with a joystick?
Theoretically, it's driven by phase-locked human consciousness, a trained pilot directly interfacing with and mathematically modulating the fabric of reality.
The mind itself is the engine's targeting system. That is, wow. I want you, the listener, to mull that over. Look up at the stars tonight and remember that empty void is a programmable machine waiting for the right source code. And the key might be inside our own heads. Thanks for taking this deep dive with us today. We'll see you next time.